Hey guys, this is Mr. Kilburn. I'm going to do an example of something called implicit differentiation to find dy dx in terms of x and y. We use implicit differentiation when we have a function and kind of the x's and y's are all mixed together, right? It's not explicitly defined. So supposing you had y equals x cubed minus, I don't know, 3x or whatever, and you had to take the derivative. Okay, it'd be pretty straightforward, a couple power rules and you're done. Well, here for this example, you have a function and you've got x's and y's kind of mixed together on the same side of the equation. So here's what you do. You take the derivative of each term, and when there's a term with a y in it, and you take the derivative, you need to tack on a dy dx or a y prime, okay? Because if I'm taking the derivative of just say like this one, okay, y prime would be 3x squared minus 3. All right, I'm taking the derivative in terms of x. It's explicitly defined in terms of x, not a big deal. But with implicit differentiation, if I take the derivative of, say, 3y squared in terms of x, well, I take the derivative 6y, but then where'd the x go? So I would need to write dy over dx. That last little bit of change that I'm not sure what it is, okay? So let me get rid of this stuff here and we will start fresh. Okay, so like I said, you start by taking the derivative of each term, which looks like this, all right? So the derivative of x cubed is simply 3x squared. The derivative of 3x squared y. So here, I need to use the product rule because x squared and y are being multiplied by one another, okay? So the derivative of x squared y, product rule, we'll call the x squared our f and the y our g. So the derivative of x squared is 2x, that's f prime, times g, which is y, plus the derivative of x squared times the derivative of y, which is just y prime. Right, so this is our, there's f prime g plus f g prime. Again, just straight power rule, product rule. Okay, plus 5xy. Well, now I've got another product rule. Okay, the derivative of x is 1. That's our f. There's our g. Plus the f, which is in this case x, times y prime, or I'm sorry, the derivative of y, which is just y prime, equals the derivative of 5, which is 0. Okay, let's clean this up a little bit. So I've got 3x squared plus, we can distribute this 3, so I get 6xy plus 3x squared y prime plus, now I'll distribute this 5 and get 5y plus 5xy prime, and again, this equals 0. All right, so again, I've got x's and y's kind of all blurred together here. Let's get our terms with just y primes by themselves on one side of the equal signs, everything else on the other side of the equal sign, factor out a y prime, and we'll be done. Okay, so the terms of the y prime are going to stay on the left-hand side of this equation. Okay, so the 3x squared y prime and the 5xy prime, they can stay over here. Everything else is moving over, all right? So I move over this positive 3x squared by subtracting. That'd give me a negative 3x squared. The positive 6xy, with subtracting, get minus 6xy. And this positive 5y, I would subtract it to both sides and get that. Okay. Next, I can factor out a y prime, which would leave me with, over here, 3x squared plus 5x equals negative 3x squared minus 6y minus 5y. And now divide out. 3x squared plus 5x equals, sorry, divide this side by 2. Let's get rid of that. 3x squared plus 5x, and I am done. Y prime equals negative 3x squared minus 6x minus 5y all over 3x squared plus 5x. Okay, if there was something else to really factor out, like if each of these terms up top had an x in them, I would factor that out because there's x's in both terms here. So I could simplify a little further, but at this point I can't. Sometimes the derivative of implicit functions can be a little messy, as is the case when you take the second derivative, then it definitely gets messy. But regardless, there's our answer. There's an example of implicit differentiation. Define dy dx, also known as y prime, in terms of x and y. Have a great day, guys.